Hello and welcome to YMT217 Programming Languages. This is the final part of Preliminaries, the fourth and final part. So we divided actually this chapter into four parts. Why? Because it has a lot of topics, and these are the topics that we will be covering the whole semester. So basically, the details that we explained earlier are linked, and today we will cover up the rest of the chapter. So what are we going to discuss? Implementation methods and programming environments. And do not underestimate these preliminaries. Why they discuss, as I said, most of the ideas we will elaborate throughout the whole semester. So let's just go through these one by one. We spoke about actually programming languages in earlier parts of this chapter. However, we will just consider deeply the types of the implementation methods of programming languages. So mainly in programming we have three categories of implementation. Implementation means how the programming language is being transferred to a machine language, or how it is translated or processed and transformed to a machine language ultimately. So how it is communicated from a high-level language, a language that we programmers know how to write, to a machine language that mostly we don't understand. It's just a series of ones and zeros. Okay, so we have three paradigms, or you can say three categories. The first one is the compilation, or the compiled language. The compiled language is literally translated from the program or the high-level language directly to machine language. Okay, and we'll explain about it. Usually such scenario is used for large programming style, complicated programming style, even maybe for creating operating systems. And that's why C programming is extremely common for creating operating systems or programs for operating systems. Actually, that is the reason. We will explain about it in a while. We have also pure interpretation or interpreted language. They are used for smaller programs usually, and the idea is like this: the programs are interpreted by another program, or actually another stage, which is we refer to by interpreter. So they are not translated to machine language. No, they have a stage in between. So we have a high-level language, then we have an interpreter that takes the process of translating or transforming the language to the machine language. Usually the idea of efficiency matters. Why here compilation is somehow faster than interpretation. I will explain why. We will have them in details. Just hold on your patience. We are speaking about the categories only now. We have the hybrid implementation system. It's actually a compromise between the two. So it's not pure compilation. It's neither pure compilation nor is it pure interpretation. It's in between. So what we do is we have some interpretation, then compilation in the process. Okay, and it's usually used for small to medium, usually bigger than this programming style, and usually less than the compiled systems. Now, what I'm saying is actually theoretical. When you go to when you decide to go for the design of big systems, then you will understand what I'm saying. So if you think about compilation, large commercial maybe applications, or large applications that require the compilation process. If your programming style or application is not that big, the scale is somehow acceptable in the small range, then you can go for pure implementation. If it is in the medium range, hybrid implementation is actually the best fit. And we will go through these slowly. Now, here is the thing. We said high-level language, low-level language, or machine language. So what do we mean actually by these? Let me elaborate. Machine language, imagine it's like a circle like this. We have the bare machine. The machine means the computer or the processor that understands only ones and zeros. There is a pulse, there is electricity, there is no +1, or what we call, logic 1, logic 0, or 5 volt, 0 volt, or whatever. So this is what we call the state of 1 and 0. high, low. So that is exactly what the machine understands. And for the machine to run, we have what we call macro instructions. And we will not speak about those now, we will delay it. So we have like a way to translate the operating system instructions to machine language. Okay, so you see it's layered structure. So we have the bare machine that understands ones and zeros. Then we have a translation or an interpretation process with the operating system. Then on top of the operating system, we have all other, you can say, programming languages that fit the operating system that we can install on our operating system. Now the idea is like this: we cannot just expect a programming language to run on directly on an operating system without having some specifications that allow it to run on that operating system. Now think about the idea of running a Java code. Now I say Java, why? Because you guys are familiar with Java. In order for you to run a Java code, you need somehow a text editor to write Java program. And then you need a Java compiler. So this Java compiler will allow you to compile the Java codes and translate them to a language that the machine understands. And for this reason, we need what we call JVM, the Java Virtual Machine. So with Java compiler, Java Virtual Machine, and a text editor, we have a Java Virtual Computer. So it's a computer that understands Java codes, translates them ultimately to somehow a source code or a code that the machine can understand. I don't want to say machine language now because we will explain why. C programming also runs the same, but what we don't need here a Java Virtual Machine, rather we need a C compiler. C is a compiled language. Java is actually, nowadays, is based on hybrid actually interpretation, and I will explain it to you why. We will take it in a while. This goes to all other languages. We have to have some way for translation, or actually a mechanism for translation. We have also some assembler for assembly language. We'll speak about assembly later on, not now, but it's extremely important as well. Now an idea, I just remembered. Maybe you think about this. How about if we just design directly a high-level language, those high-level, okay, good. I'm sorry, I need to rearrange the ideas. Why? Because I remember things while explaining. Now, why do we call these high-level language? They are high to our level. Why do we call the machine language low level? It's low to the machine language level. So now, why do not we design a high-level language on an operating system runs with a high-level language? Or why do not we design an operating system with a high-level language? It will be extremely inflexible. It's not impossible, it's possible. But the problem is translating a high-level language to a machine language needs time and effort. And that will not be flexible for installing and using a programming language that runs on top of a high-level, same category, the same type. It will be inefficient, in brief. That's why we don't do it. So we have this operating system that communicates properly with the machine, and then we can install on top of this operating system, or using this operating system, other programming language environments. The same goes to .NET languages, the 5 of them, all the 5 of them, and whatever language you imagine. So this is the idea. This is layered structure of programming languages, and also low level and high level, all of them. I mean, I asked questions from those, so think about what I explained. Please pay attention to it, and take some notes. Okay, let's go to the compilation. I didn't explain it at the beginning. I said we will go through it one by one. What does it mean, compiled language or compilation mechanism or implementation of a language? Now we have a source language. Source language means what? A text editor. Maybe we write some instructions using the formal language or the formal definition of a programming language. Then we expect it to be transferred or translated to a machine language. That's exactly compiled. So we have a source language, a source code. We translate it to a machine language. The translation in this case is usually fast, but it goes through these processes or these stages. We have the source program that's usually created by somehow a text editor. And in order for us to create a simpler contents of the source program, we write our programming code, or the code of our programming language, use the formal language definition. So we need to use the syntax and the semantic of the language that actually fits our implementation. Then what happens? It's transferred to lexical units. These lexical units are formed by a lexical analyzer, where actually they are dependent on identifiers, operators, punctuation symbols, keywords. So we create based on those lexical units. And these lexical units will be checked in terms of their syntax. Do they fit the language definition or not, the syntax of the language? And based on that, the lexical analyzer, along with the syntax analyzer, creates what we call symbol table. All the definitions of our identifiers and data that we need to use in our program in order for us to generate a machine code ultimately, after compilation, is kept here as a database. Now, after this step, what happens? The syntax analyzer, I said, uses the formal language definition. Formal language definition is exactly like any human language. It has its own definitions in terms of grammar. In order for us to understand if it fits or not, we create what we call a parse tree. So we create parse trees to see if our written instructions fit the language or the syntax of the code or the programming language in this case. Once it is done, we have an intermediate code generator. And with this intermediate code generator, we have something we call semantic analyzer. Semantic analyzer is used for actually catching the errors that we can't usually catch with the lexical analyzer, syntax analyzer. So in this case, we specifically check the logic of the instructions other than their own grammar, their meaning. And at this stage, we create an intermediate code, and this intermediate code has a reason to be created. Why? We can optimize an intermediate code much easier than the source code. Usually, source code is closer to our understanding, of the human being. It's high level. And optimizing it is possible, not impossible, but it takes time and effort, and it needs someone who's really expert in certain language in order for him or her to come up with an optimized version. But if we go to a lower level, a bit intermediate level between the source code or this programming language and the computer language, then we can optimize and automatically done. This is not done by us. The compiler of the language does it for us. So once done, we have an intermediate code. This code is similar to assembly. We will explain about assembly in a few chapters, not now. But once this code is created or generated, then we need to transfer this code to the machine code. Machine code series of ones and zeros. So we have what we call code generator, and that transfers the intermediate code to a machine code. That's exactly, you can say, the journey of compiling a compiled language source code. Okay, so explain about those. I don't want to get back to them. Let's just move forward and explain about the idea. Yes, good, I remember. So while compiling any language, if we have a compiled language, we would like to compile its source. We are not expecting that the language is covering everything on its own or by itself. No, we usually need resources from our operating system. And in order for us to load the needed resources, input, output, maybe some files also, or libraries or whatever, in that case, we need what we call load module or executable image. It's like putting together our operating system and the code in one system in order for us to share the needed resources with the programming code, with the code that we write. So if it requests these these resources, the operating system will share with it through what? The load module. And for that reason, we have what we call linking and loading, or a linker. So we use a linker to link and load whatever needed from the resources, or maybe even library packages for the program. So these terminologies are important, remember them. I ask usually questions about linkers and the load module, or what we call executable image. Think about those, okay? This is actually it for compiled languages. What kind of advantages and disadvantages? Is fast, and we don't need to translate or decode instructions multiple times. We can just compile it once because we have a simple table and we have some syntax analyzer or whatever. If the same instruction is available, we don't have to decode it and do the process over and over again. It's done once. If it's available 20, 100 times, or maybe millions of times in the same code, it doesn't have to be repeated over and over again. That saves time. It's faster in execution, more practical for large implementations. How about the problem? Now, compiled language needs to access frequently to symbol table. This is a database, so it needs to access to data, and data where? Not in the microprocessor. It's stored in the main memory, and in that case we need to have an access data transfer. It's like fetch execute in this case. So we have what we call bottleneck here. Bottleneck here means what? The processor itself is very fast. The fastest thing in your machine is the processor or the microprocessor, okay, or the CPU unit in this case. But the problem is what? In order for me to reach to the data I want to use, the data that I have to use, I have to go to the memory and fetch it, bring it. So the communication between the microprocessor and the memory slows down the process. And this is what we call the bottleneck of von Neumann. It's again the same problem with the architecture of von Neumann. We need to fetch instructions and data from the memory, and that takes time. It slows down the processor's job. Nowadays, actually, there is a solution. There's been actually a solution for this, and there is a research going on for optimizing actually the existing solution, which is actually parallel computer. Maybe you've heard of this. Parallel computer is an idea of actually running processes using the processor in parallel way, or actually dividing our processor to parallel processes. Processor is fast, is the fastest thing, so do not leave it on hold until we fetch the data and bring it from memory. No, we create parallel processes at the same time, and the processor in that case occupies its resources while if there is any data to be fetched. So I have something else to be done. That's the idea of parallel computers, and it's still also an area of research. It didn't reach to its own best form, yet it's available and it's used, okay? Pure interpretation, this is the other type, which is exactly the opposite of pure compilation or pure compiled language. In this case, we don't translate. We interpret. Interpret means what? We have a source code, and this source code, we directly translate it, not translate actually, we directly convert it to machine code, okay? Well, in that case, this process of conversion is a bit more complicated. It takes longer time. So it is 10 to 100 times slower than the compiled programs. But it is much better for catching runtime error. We can indicate, errors on runtime, and in that case, we can see and fix them. It gives you even exact line of code where the problem is. And in this case, there is also another problem. Since there is no translation, the decoding will happen over and over again. Okay? So what happens? If I have the same instruction, I'll keep decoding it, no matter how many times it's repeated, which is not the case with pure compiled language. That takes time for sure. So decoding in high-level language in this case is actually more complex than the compiled language, and it is repetitively done. Why it is more? I said it's repetitive. It's done repetitively, but the idea is why more complex. Now look at here. We have stages. Now let me get back. We have stages of decoding. and we keep, if it is decoded based on the parse3 in this case, well, we have it. So we have this instruction. Why do we need to decode it again? It's ready. You don't have to decode it. But in this case, we don't have that parse3 or that concept. So we need to decode each time. That takes time. Also, for our case here, we create what we call the symbol table, and we maintain it in certain database in the memory. Of course, not us, the program. What I'm saying is the language, how the language is doing it. In this case, no, we need our own separate, and it takes more space. In order for the language to directly convert or interpret the source code to machine code, it needs a different type of symbol table, and it requires more space. Plus, one more thing, it fixes programs based on runtime, and for that we need more collection of tools, and that also requires more space. It's more complicated in terms of its own implementation, the source code interpreter. Okay, so this is the basic idea. Now, initially it was available with languages like Perl was available initially for pure interpretation in 70s. Somehow it didn't thrive much through 70s, but it came back with scripting languages like JavaScript and PHP. The idea of pure interpretation fits these scenarios. They are somehow small in their own implementation, and they do not require much of a space, so it fits them. And here efficiency is not that much of a matter. Usually we don't write codes for operating systems or large systems. Rather, we script things to websites, and they fit in this case. Look at the presentation of interpretation. We have the source code directly interpreted, converted to the machine language, and this one is a bit complicated and takes time, as it explained. Okay. We have the hybrid implementation system. That one is actually it's a compromise between the compiled language or the compiled process and the interpreted process or language. In this case, what we do, initially we have a high-level language. This high-level language is translated to an intermediate language. When we translate to an intermediate language, what does it mean? It means this is a compilation process, right? Okay. So once we have a compiled language, like here, an intermediate, language, then we can easily interpret it. So the idea I said here is a bit complicated. Directly translating source code program or source code directly to machine code. How about if we compile it at the beginning, we transfer it to an intermediate code, which we can benefit a lot from decoding process. We don't have to repeat over and over again. Plus, it's easier for us to transfer a standard intermediate code to machine language. So in that case, we go through this kind of process. First, we compile. It's like a semi-compiled process. We convert the source code to an intermediate code. Then we easily interpret this code. There is somehow a standard for that. This will make the process much faster than pure interpretation. Of course, a bit slower than compiled language, yes, the first type. But still, in between the pure interpretation and pure compilation. I said earlier about, I said actually about Perl. This one wasn't with Perl. The pure interpretation language was not with Perl. Earlier, I mistakenly said early time of Perl programs were in pure interpretation. No, I didn't mean Perl. Actually, I meant APL, a programming language. Actually, that was the early time. Perl is a hybrid type. It's actually in between the compiled and the interpreted. So initially, it was somehow processed by a compiler, and then it's translated or not translated, it's converted or interpreted by an interpreter. Now that was the early time. However, at certain point, most of the new technologies of programming languages like Java, for example, is running by hybrid. And if you remember, we discussed this in previous semesters about Java. Java is transformed to actually an intermediate state we call bytecode. So if you have any virtual computer or whatever runs the bytecode installed on any machine, then you can run this bytecode. So you don't have to have a whole integrated environment or whatever tool that makes Java run. Why? It's enough for you to have the interpreter of the bytecode in order for you to run a Java program. But also you need the runtime system, that's the Java virtual machine, and these are important for running any Java program. So if you have the bytecode and you have the Java virtual machine, then in that case you can run any Java program, and this is exactly hybrid implementation. Okay. Look at the scenario or the illustration. We have the source code, we have the lexical analyzer again, because we have semi-compiled process. We have the lexical units we explained about, the syntax analyzer. We have the parse trees. So once we get the parse trees, then we create an intermediate code. Up until here, we explained about this in the compiled language. So we have an intermediate code. We don't have the whole idea of symbol table and optimization or whatever. Why? Because we have an interpretation process that does for us these things. So this is the idea here. Just in time. Now, just in time, we said early time of Java. I explained about this. Early time of Java is based on hybrid implementation. The bytecode, then an interpreter. So Java virtual machine will do this for you. So it will be compiled to a bytecode. Then after that, we can transfer it to a Java program or real implementation or whatever result and outcome using the Java virtual machine, or we can run the program in this case. Now the idea is like this. In more recent years, Java is not exactly based on direct concept like this. We have another system Java is built around. Not only Java, other also .NET languages. We call this language just-in-time implementation system. Just-in-time is, as I said, it's exactly a program that translates program to an intermediate language. So we need a program that translates Java to bytecode, right? So that's one of them is JIT or just-in-time. This is possible with Java. Newer versions now are using it. It's widely used for Java programs. It's also used for the 5.NET languages. 5.NET languages, when we speak about them, when we say these, we have C++ and C#, we have F#, we have Visual Basic, and we have also the scripting JavaScript, or the version actually of Microsoft version of JavaScript. We call it JScript. So these are the 5 .NET languages. They use also JIT systems. So this JIT systems or JIT system implementation translates a program to an intermediate language first, then it interprets it. So this is the idea. We create bytecodes, maybe like Java in this case, and then we can have a virtual machine. Let me show you back again here. We have like here, look, virtual machine, virtual computer. So we have virtual computer. So these are possible in that case. Java is possible for these 5 also. We have this scenario. Okay. We explain about the JIT systems. Now the preprocessors. We have an idea of importing or embedding a whole bunch of definitions or specifications in our programs using what we call preprocessors. Maybe you think about a program, I want to bring a whole collection, a whole stream, a whole library, a whole package into my program without defining them one by one. So they are defined, they have their own file of definition, and we call them preprocessors. So we can call them, we can bring them. these are widely available in different styles of programming. In C programming, they are widely available. We can include, C also C++. We can use include and define, of course with the hash code before them, to import these preprocessors. Or what sometimes we refer to them macros. Macros, why? Because they have like a chunk of instructions, a whole like pile of instructions all together defined somewhere in the file. We include them. So if you are interested in importing IO stream, a stream for input and output, you don't have to write its details. You can just include it and enclose it by these arrows, IO stream. In that case, it will be brought to your program. It's ready. You just need to use it. This is a preprocessor. In Java, we don't have exactly similar to this, yet we can import the classes that we are going to use. It's a bit similar to this case. We can import whatever class we are going to use. Or the methods, we can import the class that we are going to use some methods or all the methods from. But the preprocessors, we can create our own preprocessors, similar to Java, like you can create your own class and include it and import it if needed. These are also important. I may ask about these questions, this one also in my exams or quizzes. We have programming environments. We need to speak about the programming environments. And now we spoke about the implementation methods and categories and their own details. So what we need to do is we need to speak about the programming languages. We need to write a code. How do we write it? So programming environments, so not languages, programming environments. When we speak about programming environments, we refer to a collection of tools used in software development. So we need to develop a software or even to write a code itself. We can use a text editor, then what? Will it run with only that text editor? Most likely not. You need to incorporate this text editor with some, either a compilation process or interpretation process, or if you want to have like a peaceful running of your own code, you can use a ready programming environment. So what kind of programming environments do we have? We have Unix, the old actually version of programming environments. It was used in old like operating systems, and it has actually a wide range of tools allowing you to create different software implementation. Now, the problem with Unix is really hard to learn. In old days, if you want to learn everything about Unix, you would spend really long time. It's not easy to use. But for modern days, they created for it some development environment. We refer to development environment DE. So there are actually a bunch of development environments that can be used to make Unix look much nicer and easier, and they work actually, or they are a sort of graphical user interface. They form a graphical user interface for the user to use Unix, and through them we can conveniently use Unix. So there are still applications using Unix. More actually recently, there are like packages of integrated development environments like Microsoft Visual Studio.net. This allows you to create actually large and more complex visual environments, like codes based on visual environments. Like they have a text editor with a lot of tools, not just text editor. They have all the needed tools that allow you maybe to import even databases, to include different things, to run, to compile or to interpret, process, to debug, to even run like different testing methods. That is the idea. So for these like development environments, they are widely available for larger programming styles, maybe web applications, because we speak about .NET here, and many others, not only web applications, but just in this case, because we spoke about the .NET. We have also NetBeans. You guys are familiar with NetBeans and you know how integrated it is. It is really wide integrated development environment, and it allows us, it's very actually similar to Visual Studio. It is based on visual environment, an environment that where we write as code and we have other visual contents to add. One thing I would like to highlight, in NetBeans, for example, previously we explained about NetBeans, Java and NetBeans, we spoke about graphical user interface, but I didn't teach you, if you remember, how to create them by drag and drop, drag and add. It's possible in NetBeans. You can create a whole GUI application with just adding components to the development environment that you're using or the code that you're creating, instead of writing the code one by one. But if you ask me, as a programmer, you should write these codes rather than just drag and dropping them. Ultimately, after you finish your training or study, then you'll be able to choose to make your pick, the best choice, and see if this one goes along with you by writing codes from zero, from scratch, or if you go for graphical implementation. It's totally up to you in that case. Okay. For NetBeans, it's extremely popular for Java. Yet it is not restricted to Java. You can run different applications for programming languages like Ruby, like Python. Also, you can use it for C and C++. It's compatible also for PHP and other languages. So these are what we call integrated development environment. This is the end of this chapter. I will create another video to next chapter. Until then, have a good time. Goodbye.